China built a hotel that broke every rule of engineering. Not one hotel, 18 of them. Structures that made architects rewrite textbooks and engineers question physics itself. Buildings that cantilever backward, towers carved with holes, castles rising from coastlines, and hotels buried 88 meters underground. You're about to see how they did it. And the first one hangs a Ferris wheel between two towers 400 feet in the air. Studio City. Macau. You're standing in Macau, staring up at two glass towers. Between them, suspended 427 feet above the ground, spins a golden figure eight. It's a Ferris wheel, and it shouldn't be there. The challenge wasn't building the towers. It was installing a 17,000-ton observation wheel between them, while both structures were already standing. The wheel isn't sitting on the ground. It's mounted to the buildings themselves, mid-air, with passenger pods rotating through both loops of the figure eight. The engineering solution required steel bridge structures cantilevered from each tower, meeting in the middle to cradle the wheel. The connection points had to handle dynamic loads, weight shifting as 28 pods moved through their rotation. Each support beam was designed to flex slightly, absorbing movement without transferring stress to the towers. The wheel itself became part of the building's structural system, locked into place by tension cables and hydraulic dampers. They built a Ferris wheel that doesn't touch the ground, and it spins. But that was just a warm-up for what came next, a glass wave that refuses to fall. MGM. Macau. You walk into the Grande Plaza and look up. Above you, a massive glass wave curves across 82 feet of open space. No columns, no visible support. Just thousands of glass panels forming a flowing ceiling that looks like it's frozen mid-crash. The problem was simple and impossible. Glass is heavy. This ceiling weighed hundreds of tons, and it had to span the entire public square without a single pillar interrupting the floor below. One miscalculation and the entire thing would shatter onto guests. The solution hid in plain sight. Engineers designed a tension cable system embedded within the curved framework. Steel cables, pulled tight like guitar strings, ran along the perimeter and through the structure itself. Each cable distributed weight to the exterior walls, never letting the load concentrate in one spot. The glass panels weren't just sitting there, they were held in a web of calculated tension, every piece pulling against every other piece. The frame curved deliberately, using geometry to redirect force outward instead of down. You're standing under hundreds of tons of glass, and physics is the only thing holding it up. But the next building didn't just defy gravity with glass, it stacked containers in ways that made architects question geometry itself. MGM. Cotai. You step into the lobby and look up at something that shouldn't work. The building rises in stacked blocks like shipping containers piled on top of each other, each section offset from the one below. Some boxes jut out, others pull back. The engineering challenge was building a tower that refused to stack vertically. Each offset block created cantilever sections of building hanging in space with nothing underneath them. Traditional construction stacks weight directly down through columns. This design threw weight sideways. The solution required massive steel transfer trusses at every transition point where the blocks shifted. These horizontal beams, some spanning 3 stories tall, caught the cantilevered weight and redirected it down through the offset columns below. The reinforced concrete core anchored the center, but couldn't handle the eccentric loads alone. Steel outriggers extended from the core into each protruding block, acting like arms bracing against the cantilever. Where blocks stacked inward, engineers added tension cables through the floor slabs, pulling the overhanging sections back toward the core. Every offset required custom calculations. No two transitions used the same structural solution. They built a tower that looks like it's falling apart. The engineering is what keeps it together. But the next building made an even bolder choice. It decided to bloom as it rose. Grand Lisboa. You're looking at a building that gets wider as it climbs. The base spans 295 feet. The top stretches 427 feet. 853 feet tall. It's a lotus flower blooming in steel and concrete. And every floor defies the most basic rule of construction. Don't build outward when you're building up. The engineering problem was fighting physics at every level. Traditional skyscrapers taper inward to reduce wind load and keep the center of gravity stable. This tower did the opposite. Each floor cantilevered further out than the one below it. The higher you went, the more the building wanted to tip over. The solution started at the core. A reinforced concrete cylinder, 30 feet in diameter, rose through the entire height, the spine of the lotus. From this core, radial steel trusses extended outward at each floor, growing longer as the building rose. These weren't simple beams. They were three-dimensional frameworks, some 3 stories deep, engineered to handle both the cantilevered floor weight and the torsional forces from wind trying to twist the building. Each truss transferred its load back to the central core through post-tensioned cables, steel tendons pulled so tight they turned compression into tension. At the peak, a tuned mass damper weighing hundreds of tons swung on pendulums, counteracting the building's sway in high winds. They built a flower that opens as it grows, and engineering is what keeps it from falling closed. But the next hotel abandoned vertical towers entirely and built a ring standing on its edge. Sunrise Kempinski Hotel. You're staring at a golden ring, 325 feet tall, standing upright on its edge. A perfect circle rising from the shore of Yankee Lake. No base wider than the top, no taper. Just a continuous loop that looks like someone rolled a coin to the water and it decided to stay standing. The engineering nightmare was obvious. Circles don't stand on edge. The structure wanted to fall in every direction at once. Wind hitting the curved surface created pressure on one side and suction on the other. The ring shape meant there was no stable base, no pyramid foundation to anchor against. Every calculation fought geometry. The solution required 2 structural cores built into opposite sides of the ring, like pillars hidden inside the circle. These weren't centered. They were positioned where the ring touched the ground and where it curved overhead, creating 2 anchor points 180 degrees apart. Steel framework connected these cores, following the circle's curve, forming a rigid tube. But a tube alone would buckle. Engineers added internal bracing diagonal steel members crisscrossing the interior like a bicycle wheel's spokes, distributing force around the entire loop. The foundation went down 100 feet through soil into bedrock, with piles driven at angles to resist lateral movement. The ring wasn't just resting on the ground, it was locked into the earth. They built infinity and made it stand up. But the next structure took that impossible curve and opened it over water. Hilton, Hujo Nanshan. You're looking at a sphere rising from Taihu Lake, not a dome. A complete sphere like someone took a perfect ball, sliced off the bottom, and set it on the water. 302 feet in diameter. The curvature is continuous, wrapping around itself with no corners, no edges, no flat surfaces, just pure geometry floating above the lake. The engineering problem was building a shape that offers no structural advantages. Spheres are strong under internal pressure. Submarines, pressure vessels, they work when force pushes outward. But a building sphere experiences gravity pulling everything down and wind pushing horizontally. The curved surface provided no flat floors, no vertical walls, no right angles for conventional construction. Every room inside required a custom layout. Every floor slab had to curve. Every structural member followed a different radius. The construction started with a steel space frame, a 3-dimensional lattice of triangulated members that formed the sphere's skeleton. These weren't standard beams. Each piece was custom fabricated to precise angles, connecting at nodes calculated by computer modeling. The frame created a rigid shell, distributing loads across the entire surface rather than down through columns. Concrete floor slabs poured inside this framework, each one curved to match the sphere's geometry. The exterior cladding followed aluminum panels shaped to the radius, mounted on a secondary framework that tracked the primary structure. At the base, where the sphere met the water, a ring foundation spread the weight across the lakebed. Piles extended down into bedrock, positioned around the perimeter to resist both vertical loads and lateral forces from wind trying to roll the sphere. They built a ball and made it a building. But the next hotel didn't stop at one impossible shape. It carved holes straight through a 40-story tower, Intercontinental Shanghai Wonderland. You're standing at the edge of an abandoned quarry, looking down 288 feet into the earth. At the bottom, carved into the rock face, sits a hotel. 16 floors below ground level, 2 of them underwater. They didn't build up, they built down. The engineering challenge was building below the water table in a pit that spent decades filling with groundwater. Every conventional method assumes you're working above ground where water drains away and soil compresses downward. Here, water pressed inward from all sides. The deeper they dug, the more pressure pushed against the walls. One crack in the structure and the entire hotel would flood. The construction started with the walls. Engineers poured reinforced concrete retaining walls directly against the quarry rock face, 3 feet thick, anchored with steel bolts, drilled 30 feet into bedrock. These walls had to hold back millions of gallons of water trying to seep through fractured stone. A waterproof membrane system wrapped the exterior multiple layers of rubberized fabric and bentonite clay that swelled when wet, sealing any gaps. The base slab went down 10 feet thick, a solid concrete platform designed to resist uplift from groundwater pressure trying to push the building upward like a cork. For the underwater rooms, they used laminated glass panels, multiple layers fused together, rated to handle pressure at that depth. Each panel was tested to 3 times its working load before installation. They built a hotel where swimming pools look up at fish, and the walls hold back a lake. But if building downward seemed impossible, the next hotel made it look simple by defying wind with glass. WYN Macau. You're standing in front of a curved glass tower that bends like a sail in the wind. The facade isn't flat. It's a continuous wave of glass panels, each one angled differently, wrapping around the building's crescent shape. 51 stories, 600 feet tall, and every surface is reflective glass catching light from the harbor. The engineering problem was the curve itself. Flat glass is easy. You mount it to a grid and move on. Curved glass facades require every panel to be custom cut, every angle calculated, and every mounting point engineered for different loads. The crescent shape meant the windward side took direct pressure while the leeward side experienced suction. The glass had to handle both without flexing enough to crack. The construction solution started with a steel subframe behind the glass. This wasn't a simple curtain wall system. Engineers designed a 3-dimensional framework that followed the curve, with mounting brackets positioned at precise coordinates for each glass panel. Every bracket allowed for thermal expansion. Glass expands and contracts with temperature changes, and if locked rigid, it shatters. The panels themselves were laminated multiple layers bonded together so that if one layer cracked, the others held. Structural silicone sealed the edges, flexible enough to absorb movement, but strong enough to keep panels locked in compression. The entire facade hung from the concrete floor slabs above, each floor supporting the weight of the glass below it, transferring load down through the building's core. They wrapped a crescent in glass and made it strong enough to face typhoons. But the next structure didn't settle for one curve. It built 2 that mirror each other. Sheraton Huzhou Hot Spring Resort. You're looking at twin horseshoes, 335 feet tall, facing each other across water. Perfect mirrors. The north tower curves one way. The south curves opposite. The gap between them spans 200 feet, and they had to be built identical. The engineering challenge was precision at scale. A 1-inch error on floor 10 becomes a 10-foot gap by floor 30. The curves had to match. The angles had to align. Both towers had to rise simultaneously from a shared foundation in the lakebed. Parametric design computer modeling calculated every curve coordinate before construction started. Both towers used identical prefabricated steel frames, laser measured and tagged. On site, cranes lifted sections guided by GPS positioning accurate to millimeters. The foundation platform, a massive reinforced concrete slab with piles into bedrock, kept both towers locked to the same reference point. Surveyors checked alignment daily against the digital model. Steel tension cables ran through both structures, post-tension to pull the curves into final geometry. Deviations were corrected immediately. Shims, adjusted connections, retensioned cables. They built 2 mirrors in steel and concrete and made them reflect perfectly. But the next hotel took structural risk even further by carving holes straight through a skyscraper. Morpheus Hotel Macau. You're staring at a building with 3 rectangular voids cut straight through it. Not windows, holes. Empty space where 40 stories of structure should be. The tower rises 530 feet. You can see sky through the middle at 3 different levels. The engineering problem was removing the parts that normally keep buildings standing. Traditional skyscrapers stack columns and floor slabs vertically. When you carve voids through that system, loads have nowhere to go. The solution was the world's first free-form high-rise exoskeleton. All structural support moved to the exterior. A steel frame wrapped the perimeter, following organic curves around the voids. Computational analysis mapped stress flows, identifying where steel needed to go. 12 massive custom nodes, junction points where steel members converged, each weighed up to 70 tons. Forged as single pieces, lifted into place, welded to connecting beams. The exoskeleton carried all loads to the foundation, bypassing the voids. Inside, floor slabs cantilevered from the perimeter frame with no columns beneath them. They carved holes through a skyscraper and made the outside hold up the inside. But the next building's danger wasn't what it removed. It was what it hung above your head. Galaxy Macau. You walk into the diamond lobby. A 50-ton chandelier hangs above 21,500 square feet of open space. Steel trusses hidden above the ceiling hold it. Bundled cables drop down to an internal skeleton that keeps the crystal balanced. Outside, 3 golden towers rise from a shared podium, each a different height. Facades wrapped in curved gold-toned glass. The structural challenge was supporting 3 separate towers above massive column-free spaces: lobby, casino, convention halls, all requiring clear spans. Engineers designed transfer trusses at the podium roof, some 3 stories deep, redirecting tower loads horizontally before sending them down through perimeter columns. Each tower's reinforced concrete core provided lateral stability. Outrigger trusses at mechanical floors connected cores to perimeter columns, stiffening the structure against typhoon winds. The curved glass facades mounted to steel subframes with brackets allowing thermal expansion. The foundation, a massive reinforced concrete mat, spread the weight of all 3 towers into the ground. They built 3 towers on one base, each one different, all of them standing. But the next hotel multiplied that challenge: 8 towers shaped like petals blooming from narrow stems. Sanya Beauty Crown Hotel Complex. You're looking at 8 towers shaped like flower petals, each 23 stories tall, arranged in a crown formation. They bloom from narrow stems, each tower barely a quarter its width at the base. 8 buildings that get wider as they rise. The engineering challenge was building upside-down pyramids. Each floor cantilevered outward from the one below, creating petal curves that flared at the top. The weight hung beyond the support beneath it. All 8 towers had to balance on their stems simultaneously. Reinforced concrete cores formed each tower's spine. Steel frames extended from these cores at every floor, growing longer as the building rose. Diagonal bracing transferred cantilevered weight back to the core. Post-tensioned cables ran through floor slabs, pulled tight to counteract bending. The narrow stems were solid reinforced concrete, handling eccentric loads from the flared towers above. A shared podium connected all 8 through a continuous foundation with deep piles beneath each stem, anchored into bedrock. They built flowers in concrete and made stems hold petals. But the next structure didn't cantilever floors, it suspended entire buildings between mountains. Banyan Tree, Nanjing Garden, Expo Resort. You're looking at villas hanging between hillsides, not built on slopes, suspended across valleys with nothing beneath them but air. Steel and glass structures bridging gaps that span hundreds of feet, hovering above the ground like something from a floating city. The engineering challenge was building habitable spaces as spanning structures. Bridges are designed to be crossed, not lived in. These had to support rooms, furniture, people, dead loads, and live loads while stretching between 2 anchor points with no intermediate support. The solution was steel bridge framework anchored deep into both hillsides. Foundation drilling penetrated rock faces, creating concrete-filled shafts that locked the bridge ends into solid stone. From these anchors, steel box girders extended across the span hollow rectangular beams, welded together, forming the primary structure. The villa buildings didn't sit on top of this framework. They were built into it, floor systems integrated with the bridge deck, walls attached to vertical supports rising from the girders. The steel structure handled all spanning loads. Tension cables ran through the framework, post-tensioned to reduce deflection and prevent sag. Each villa became part of the bridge's structural system, the building and the span working as one unit. They build bridges you can sleep in, anchored to mountains on both ends. But the next hotel created something even stranger, a disc that appears to float above the ground. Chimelong Spaceship Hotel. Zhuhai. You're staring at a disc, 1,043 feet in diameter, hovering above the ground. A UFO in concrete and steel, rising from a narrow central base with edges hanging in space. The engineering problem was supporting a circular building from a single point. The disc wanted to sag at the edges. Traditional buildings stack vertically. This one spread horizontally across 1,000 feet. A massive reinforced concrete core anchored the center. Radial steel trusses, some 3 stories deep, extended like spokes to the perimeter. A continuous steel ring connected all radial beams at the outer edge. Hidden columns supported the ring at intervals, concealed by curtain wall cladding. Floor slabs hung from the radial framework. Deep foundation piles beneath the core anchored into bedrock. They built a disc on a center point and hid what keeps it from falling. But the next hotel didn't hide its engineering. It made an icon part of the structure. The Parisian Macau. You're looking at the Eiffel Tower, rising from the hotel's entrance. 492 feet tall, half scale of the Paris original. Wrought iron lattice anchored to the building's foundation, standing as the centerpiece of the entire complex. The engineering challenge was supporting a tower that massive as part of the hotel structure. 7,000 tons of steel framework had to transfer its load through the building's base, through casino levels, lobbies, occupied spaces, down to bedrock. The tower wasn't decorative. It was structural deadweight, pressing down on everything beneath it. A reinforced concrete foundation platform spread the tower's load across the site. Steel framework replicated the Eiffel lattice diagonal members, forming the iconic taper, horizontal platforms at observation levels, all bolted together. The base integrated directly into the casino floor level. Isolated load-bearing columns beneath the tower transferred weight straight down through the building, separate from the columns supporting hotel floors. The foundation extended deep, with pile groups driven into bedrock to handle the concentrated loads. They built half the Eiffel Tower on a hotel foundation and made the ground beneath it strong enough to hold Paris. But the next hotel didn't just copy one landmark, it built an entire Italian city under one roof. The Venetian Macau. You're standing inside 10,500,000 square feet, the 7th largest building on Earth. Casino, shopping mall, convention center, hotel towers, and indoor canals with gondolas beneath a painted sky. Venice in a box. The engineering challenge was spanning massive column-free spaces. Casinos needed unobstructed floors. Shopping corridors needed open sightlines. Canals filled with water had to sit on upper floors not designed for that weight. Post-tensioned concrete slabs cables pulled tight through concrete allowed thinner slabs to span longer distances without columns. Steel trusses bridged gaming floors, some spanning over 200 feet. For the canal level, reinforced floors handled hundreds of thousands of gallons. Waterproofing membranes sealed beneath decorative surfaces. Structural concrete canal bottoms rated for water load and gondola traffic. Hotel towers rose from the Podium base, their loads redirected through transfer structures around the open spaces below. They built Venice inside. Canals, towers, piazzas, all under one roof. But the next hotel didn't recreate history, it shattered it into 20,000 pieces. Hotel Eclat Beijing. You're looking at 20,000 pieces of glass covering the facade. Not windows. Individual glass sculptures, each a different size, angle, shape. A cubist explosion, frozen in mid-blast. The engineering challenge was mounting 20,000 unique pieces. No two identical. Every angle custom. Every bracket calculated individually. And the entire surface had to handle wind loads hitting protruding glass. A steel subframe backed the facade, a three-dimensional grid mounted to concrete. Each glass piece got a custom bracket designed for its specific angle and weight. Computer modeling calculated loads for every piece: wind pressure, glass weight, thermal expansion. Brackets allowed movement through flexible connections. Glass expands and contracts with temperature. Locked rigid, it shatters. Structural testing verified wind loads on the faceted surface. Irregular angles created turbulence. Flat facades don't experience. They covered a building in 20,000 sculptures, each one engineered separately. But the last hotel didn't fragment reality. It built an entirely different one. The Castle Hotel Dalian. You're standing on the coast of China, staring at a Bavarian castle, not inspired by one. A full-scale Gothic castle. Towers, turrets, stone walls, spires built as if lifted from medieval Germany. Except it's here, and it's engineered for earthquakes and typhoons. The challenge was replicating medieval architecture in a modern seismic zone. Gothic castles used massive stone walls as load-bearing structures. But stone doesn't flex, it cracks. China's coast demands structures that survive earthquakes and typhoon winds. A steel skeleton hid inside period-correct stone. Steel frame columns, beams, lateral bracing provided all structural support. The stone exterior was cladding, not load-bearing, attached with anchors allowing independent movement. During earthquakes, steel flexed. Stone moved with it, without carrying stress. Spires and towers, traditionally solid stone, became composite structures with steel cores and stone exteriors wrapped around them. Foundation piles drove deep into bedrock beneath coastal soil, anchored against vertical loads and lateral forces. They built a medieval castle with a modern skeleton. Stone outside, steel inside. You just saw 18 hotels that broke every rule. They cantilevered backward, carved holes through towers, built downward into quarries, hung over water, and made spheres stand upright. China didn't push engineering limits. They erased them.